Brilliant. Okay, thank you. So today is part 2 of the webinar on complex numbers. So you can view a recording of the first one. It should be in your Google Classrooms, and it should be in your it should be available on our website and on the Telegram group. So please please do that. So we're waiting for the guest speaker. So it's the same speaker as last week, David Vaccaro. He's done he's written the assignment for you, and we're just waiting for him to join. Right. Very good to see familiar faces, familiar names. If you have any questions for me, you can ask me while we're waiting for David. Happy to answer. There's a question. Hi, this is my first webinar. Could you explain what I have missed so far? This is the fifth this is the fourth webinar. Okay, so we had 2 webinars on physics, and we had 1 webinar on maths. So the webinars on physics were both on circular motion. You can watch the recordings. They are available in Google Classroom, and they are available in the Telegram group. Now, if you can't find them, just send me an email. I'll point you in the direction. And yes, so you will have tutorials with tutors in small groups starting in October. So that would probably roughly be 22nd, 23rd of October. You start tutorials in small groups with a teacher. Okay, and you have every week you'll have a tutorial until the 1st of May. Okay, when the program finishes. And your tutors will be marking your work. And this is for those who have successfully completed assignment 1 maths and assignment 1 physics. So the deadline is the 16th of October. If you complete assignment 1 physics and assignment 1 maths, and you pass the threshold that we don't know yet, it's like a marking scheme, and you get in to the COMPOS program, and you will have a tutor. If you're not successful, you will still have me. You'll still have these webinars. You will still have access to all materials, and you can study on your own. But the only thing missing would be the tutorials. Okay, I think David is here. You don't need to. No, you don't have to watch them, all of them. If you can solve the problems, if you see the problem sheet and you can do all of them, just do them and submit. That's all you need to do. So you don't. It's not mandatory to watch or anything, but it helps. It helps.
I'm just trying to share my screen. I think I'm not a host. I think I'm not
yes,
a host yet.
I will make you a host. Okay. I just need to find you. I just need to find you in the list. David, yes. So now you're the host, David.
Excellent. So I should be able to share my screen. Can you hear me?
I can.
Super.
Do other people can you hear David?
Okay. And can you see my screen?
Yes.
Brilliant. Okay, I'm going to start with a little bit of a discussion about abstract mathematics. And in some ways, this will be a kind of summary of your story of maths since sort of early childhood, really. So I want to talk a little bit about closure properties. So what do we mean by closure? Well, if there's some set, okay, so let S be a set, and star an operator on this set, and I'll specify that it's a binary operator. And what do I mean by a binary operator? Well, that means that it maps pairs of elements of S to something. And what we say is that S is closed under star if A star B is a member of S for all A and B in S. Okay. One thing which I'm doing at this point is I'm getting you ready for what maths will look like at university and in sort of advanced books when you read them. Okay, university maths books don't look like school textbooks with lots of blocky bits with colors where they talk through how to do a question. They're written in quite a formal style, and the notation becomes, you know, more general, more abstract, and it can take a little bit of time to process. So I've written this quite formally. So S is a set, star is a binary operator which maps pairs of elements of S into something, and we say that S is closed under star if A star B is in S, and that if it's closed under star, the thing which star maps into is S itself. So the range of this operator is S. Okay, question, and I'll put it out to the chat. What do you think is the first binary operator that you meet in your life? Now, my daughter is 6 years old, and I expect my daughter will come home from school at some point, so there might be noises off. What binary operator do you think she knows? Excellent. Lots of people are saying addition. And what type of numbers do you think my 6-year-old daughter knows how to add? So someone suggests integers. Now, my daughter's not quite reached integers. Yeah, someone has said natural numbers. Excellent. Okay, so our first binary operator is addition. And the first time we meet addition is it maps natural numbers to natural numbers. And if I take any two natural numbers, like 2 plus 3, then that gives me a natural number. So we say that n is closed under addition. What do you think the second binary operator that my daughter will meet? And she's only 6, so she doesn't meet it. Excellent. The second one that most children meet is indeed subtraction. Okay, and very soon, actually, my daughter will learn that if 2 plus 3 equals 5, then that means that 5 take away 3 is equal to 2, or 5 take away 2 is equal to 3. But what is the problem with subtraction? So is subtraction, if I try to define subtraction on pairs of natural numbers, is this operation closed? Yes, you can get a non-closed natural number. So what subtraction sum will make my daughter cry? So she'll be able to do 5 take away 3, she'll be able to do 5 take away 2, that all stays within the natural numbers, but at some point my daughter will meet 2 take away 5, and the teacher will say, you start with 2 sweets, you take away 5 sweets. So you can sort of picture her playing with sweets. She's got her 2 sweets, she takes away 1, she takes away 2. How's she going to take away the 3rd, the 4th, and the 5th? Okay, now we know the answer. Okay, we know that the natural numbers are not closed under subtraction. In order to create closure, okay, we need to create a new class of numbers. Okay, so if the natural numbers, I need for subtraction to be defined, I need to introduce negative numbers. And so -3, it's a bit annoying that the operation subtraction and the negative of a negative number are written with the same symbol. They're both written with a minus sign. But this -3 is a different type of number. It's an integer. Okay, so what we say, okay, and you'll meet this if you're a mathmo rather than a physicist, you'll meet this type of language a lot when you go to university, is we say that n is not closed under subtraction. Okay, but z is closed under addition and subtraction. We're going to do some problems later, but this is just a little bit of, I think this is a useful overview of the sort of history of mathematics. So Z endowed with addition, it is closed. Okay. There are inverses. Sorry, there's an identity element. There's a very special natural number 0, which is such that a plus 0 is equal to a. There's inverses. So if I add a and negative a, I get back to 0. And it's also got a property called associativity. And that means it doesn't matter the order in which you bracket things up. So a plus b plus c is the same as a plus b plus c. Now, something which mathematicians do an enormous amount, but physicists do it as well, is they give names to kind of algebraic structures. Now, this is not something which I would expect you necessarily to have seen, but you might have glimpsed it out of the corner of your eye. Does anybody know the name for the mathematical structure that has got, which is a set with a binary operator, which has got these 4 properties that you stay within the set, you've got an element that doesn't do anything, you can always put 2 elements together to get back to the identity, and it doesn't matter the order in which you bracket things up. This is a special type of algebraic structure. No, I'm not surprised people have known it. But these 4 properties together is called a group. So any set with these operations is called a group. Now, the addition of integers has got a special extra property, which is that a plus b is the same as b plus a. And so the binary operator commutes. And so that's called a commutative group or an abelian group. Okay, next question. What's the next binary operator that you meet in your life? So you see addition, you see subtraction, you then realize that if subtraction is to work, you need to do negative numbers. You do multiplication. Excellent. Okay. So let's think about this. Is this closed? So if I endow pairs of integers with multiplication, does that always give me an integer? Well, yeah, if I multiply positive integers, 2 positive integers together, I get a positive integer. If I multiply 2 negative integers together, I get a positive integer. If I multiply a positive and negative, I get an integer, but I'll always get an integer. Okay. Let's see if the integers with multiplication is a group. So we've got that the integers with multiplication is closed. Next question, is there an identity element? So an identity element would be a special element, which when we multiply it by an integer, it would just do nothing. We would just stay at Z. Yeah, good. Okay, there's a special identity element, which is called 1. Next question, inverses. Okay, so is there for each integer, is there an inverse integer that will take me back to 1? So if I've got an integer Z, is there always an integer let's call it 1 over Z? which will take me to 1. No, excellent. Okay, no, there's not. Ah, right, good. And people have identified 2 problems. So someone give me an integer. Well, let's take the average integer. Okay, what's the multiplicative identity of 2? So what do I need to multiply by 2 in order to get to 1? A half. Okay, so if I've got multiplication, if I've got the integers with multiplication, I can't always get a multiplicative inverse. Now, what that means is I can't always divide. So we've got a very similar problem with integers with division that we had with natural numbers with subtraction. So what type of numbers do I need to introduce in order to have multiplicative inverses? So in order to get additive inverses, so to allow subtraction, I needed to introduce negative numbers. Excellent. In order to get division, okay, I need to introduce rational numbers, and then I've got division. Sorry, there's just a knock at the door, which I just need to take quickly. I'm just going to ask you, are the rational numbers a group? So look at the 4 group properties here and tell me whether the rational numbers are a group under multiplication. Oh, hello. Hello. So let's okay, so lots of people have said yes, the rational numbers are a group. So let's check. Is it closed under multiplication? Well, yes, if I multiply 2 fractions, I always get a fraction. Is there an identity element? Well, yes, we've already seen it. There's 1. 1 times a over b is just a over b. Multiplicative inverses, well, a over b times b over a is equal to 1. And associativity, yes, if I multiply QR times S, that is the same as QR times S. So it looks like it's a group, but it's not, because it's not quite the case that everything has a multiplicative inverse. Is there any rational number that doesn't? Yeah, good. There's no 1 over 0. Okay, so if I take away 0, so if I take 1 away from the natural numbers, then, sorry, 1 away from the rational number, 0 away from the rational numbers, then I've got a group under multiplication. But Q is also special, okay, because Q has got addition and Q has got multiplication, and these are not completely separate operators. Yeah, we can open brackets. We've got this distributive property. mathematicians are keen to give names to things. Okay, and a set which has got these two binary operators, which are also distributive over one another, is called a field. Okay. So with the rational numbers, we can add, we can multiply, we can subtract, and we can divide except by 0. Yeah, does 1 over, so the question is here, does 1 over 0 also mean it couldn't be closed if division was allowed? Yeah, so the rational numbers are not closed under division. They are closed under, the rational numbers are not closed under division. They are closed under multiplication, because if you multiply by 0, you stay rational. Okay, now why don't we stop with the rational numbers? Okay, we can add, we can multiply, we can subtract, we can divide, and for a long time my daughter's going to be happy with rational numbers. But when is she going to hit a problem? When is she not going to want to, when is she going to realize that rational numbers are not enough? Yeah, when she hits irrationals. Yeah, so we find that the square root of 2 is not rational. Yeah, so in order to make a square root operator that acts on every positive rational number, we can't do it. So we invent the reals. Okay, what's the limitations of the reals? Okay, and for a long time the reals seem like enough. In particular, they're closed under limits. But we cannot get the square root of negative numbers. So square root -1 does not exist. So the complex numbers are a field, and they're a very special type of field. So when do we run out of complex numbers? Okay, so what's the sort of, there's a very particular special type of closure that complex numbers have. And that is that if I write down any polynomial, yeah, then the roots are always complex, okay, are always in C. And that's, Lottie, I'm teaching, I'm doing this webinar. And we say that the complex numbers are what is called algebraically closed, okay? And that deep result, so this result is called the fundamental theorem of algebra. Shows that the complex numbers, okay, are such that we'll never, well, if we restrict the polynomial operations, we'll never require another set of numbers. So they satisfy they satisfy us for a large amount of our mathematical lives. There are other structures which are numbers in some sense, that they have an addition and a multiplication, things like the quaternions, but you tend to lose certain nice properties like commutativity. But so the moral is that your story of your mathematical life is an ever-increasing family of numbers, and that permits more and more things to be closed within that family of numbers. Okay. Can you give me a so we're just going to think a little bit more deeply about closure. Can anyone give me a subset of natural numbers, of complex numbers that is closed under multiplication? And this is a sort of question one can imagine on a first problem sheet at university. So it's not a computational question, but it's a question which tests sort of processing of a kind of abstract concept like closure. So any suggestions for a set of numbers that is closed under multiplication? Yeah, the reals is one. Yeah, so because if real numbers are complex numbers, and if R is real, and if S is real, then R times S is real. Okay. There's another natural family of complex numbers, which is not a subset of the reals, which is also closed under multiplication. Right, someone suggested even reals. But what does even reals mean? Even and odd is not a property of real numbers. It's not a property of real numbers. It's a property of natural numbers. Yeah, it makes no sense to say that pi is even or odd. Well, someone said even integers. Even integers, yeah, they're closed under. Yeah, even integers would be closed under multiplication, but they're a subset of the reals. There's an important family of real complex numbers, so real and non-real numbers, which is closed under multiplication. Imaginary numbers are not closed under multiplication because the most natural imaginary number I, if you multiply it by itself, is no longer pure imaginary. A very important subset of the complex numbers which is closed under multiplication is, well, let's take a complex number Z and a complex number W. We know that the modulus of ZW is the modulus of Z times the modulus of W. Does that give a clue to an important family of complex numbers which is closed under multiplication? Well, what would happen if Z equals 1 and W equals 1? What could we say about ZW? Yeah, so the modulus of ZW is also equal to 1. So this set of complex numbers is closed under multiplication. Okay, and one way we can see that it's closed under multiplication is that if you've got a modulus of 1, you could write z equals e to the I theta. So if I pick two complex numbers in S, z and w, I can write z as e to the I theta, w as e to the I phi, and zw is equal to e to the I theta plus phi. So algebraically, multiplication of complex numbers in which have got modulus 1, algebraically, it's very similar to just real numbers added with addition. And this is getting into the sort of very much the sort of heart of a sort of maths degree. Yeah, that if we map the set of real complex numbers of modulus 1 to the real numbers, where we map e to the I theta to theta, then if we multiply complex numbers, we just add arguments. So the output is theta plus phi. So it looks like S is very similar or algebraically equivalent to the real numbers. But there's a slight, and again, this is something which you study a lot in a maths degree. There is a difference in structure between the set S and the real numbers. Can anyone see what it is? Is it as simple as all that, just to say that a complex number can be written as e to the I theta? Is there only one choice of an argument for a complex number? No, because we always choose the argument of a complex number to lie between negative pi and pi. But then when we add arguments, we sometimes fall out of that range. So you don't actually strictly add arguments. You only add arguments if you associate a real number that differs by 2 pi as being the same real number. So what you really do when you map a complex number to its argument is you map it to the real numbers, and we say quotient of 2 pi, which means that if two numbers differ by two real numbers that differ by 2 pi, we regard them as the same thing. Now, what does this mean? This r over 2 pi? Well, it means that we're taking the interval of real numbers between negative pi and pi, but we're regarding two numbers which differ by pi as being the same. So it's a little bit like gluing negative pi and pi together. Okay, now I'm going to gloss over this a little bit, but hopefully you can see that this, yes, someone's made a really good observation in the group chat where it said it's like modular arithmetic. Yeah, so my daughter's also learning to tell the time. Okay, now she knows how to, if she adds times together, if it's 8 o'clock and I say, what's the time in 2 hours time? She can tell me that it's 10 o'clock. If I say it's 8 o'clock, what's the time in 6 hours time? She would want to go to 14, but then she has to remember that 14 is glued together as with 2 because they differ by 12. Okay, so with sort of modular arithmetic with the clock, you count round in a circle and then you glue 2 and 14 together. Okay, now with arguments of complex numbers, you're doing it not just with whole numbers that you glue together, but you're doing it with a real line together. Okay, but that should make kind of intuitive sense. Again, to my daughter, it should make sense that if she's got a length of string, if she wants to turn it into something which is topologically a circle, she knows that she just needs to stick these two ends together. Okay, and that is a reflection of this algebraic fact that algebraically the unit circle is endowed with multiplication, is a little bit like the real numbers associated with addition, but when you stick real numbers together when they differ by 2 pi, which turns it from a line into, surprise, surprise, a circle. Okay, and that association between the algebraic structure of something and its geometry is super important within a maths degree. It also, at the higher levels of physics, also becomes super important when you consider when you consider symmetries. Okay, so symmetries kind of have this sort of gluing together, and so there's kind of symmetries that you've heard of in physics of spin and things like that are, you can have some visualization here. There's an association between the algebra and the geometry, and I just wanted to hint at that in this section. Okay, so that's what I wanted to do first. I just wanted to sort of give you a sort of window into sort of conceptual theoretical mathematics. So we've talked a little bit about closure properties and fields. I now want to look at a problem that looks almost unrecognizable to have anything to do with complex numbers. Okay, and the equation that we are going to consider is, I want to find, can we find all natural numbers that satisfy a squared minus 2b squared is equal to 1. Okay, so just first off the bat, can anybody tell me any pairs of natural numbers that satisfy a squared minus 2b squared equals 1? I think if everyone scratches their head and stares at this equation for long enough, they'll be able to find an a and a b. Yeah, a equals 3, b equals 2. Yeah, 3 squared minus 2 times 2 squared is 9 minus 8, which is equal to 1. I reckon if people really scratch their head, someone said a equals root 2, b equals 1. No, because I want natural numbers. But I reckon if people really scratch their head and they think about other square numbers they know, they might be able to find a second one. I'll give people. Mm, 10 and 7 doesn't quite work because 100 take away 2 times 49 is equal to 0. Oh, someone's found a really cute one, which I'm not going to quite allow. 1 squared minus 2 times 0, that's definitely equal to 1. Okay, the next one, which you might have spotted, 17 squared is 289. 12 squared is 144. So 2 times 12 squared is 288. So 17 and 12 would also have worked. Okay, now this equation is a famous equation. It's called Pell's equation. For those of you applying to do maths, it's come up on quite a few math papers in various guises. That's partly because just mathematicians love Pell's equation. Now, how are we going to solve it using, not using complex numbers, but using sort of complex style ideas? So, you know, earlier on, we said that the rational numbers weren't complete because of there were irrational numbers like the square root of 2. Now, this is a really important maths idea and something which one does a lot in pure maths at university. So my question is, what is the smallest field? Okay, so remember, a field has got all the 4 mathematical operations: addition, multiplication, subtraction, and division not by 0, that contains all the rational numbers, but also has root 2 in it. So someone's come up with a really good idea. Could you sketch it as a hyperbola and find the solutions from there? It's very similar to asking if I could find all rational numbers that satisfied a squared plus b squared equals 1. Now there's lots, you know, could I just draw the circle and then look at the rational numbers on that circle? Well, yes, but only if I can find some process to find them. But you're right, it will correspond to whole number points on a hyperbola. But let's consider this question. What is the smallest field that contains Q, but also has root 2 in it? So in other words, instead of like dealing with all the irrational numbers to create the real numbers, let's just create a field that would allow us to take the square root of 2. Well, hopefully you would agree with me that any the numbers of the form a plus b root 2 is a field. Okay, now why? Well, it's very similar to when we showed, like in the complex, when we deal with complex numbers, when we show that complex numbers are a field. Okay, so addition is easy. Because you just add, like in complex numbers, you add real and imaginary parts. Here you add rational parts and then multiples of root 2. Subtraction is easy. Multiplication, it's definitely closed under multiplication. Again, like complex numbers, most of the parts of the brackets are relatively boring. So you get an AC, you get a BD root 2, you get a BC root 2. The exciting one is when the root 2 hits the root 2. Why does the root 2 hitting the root 2 keep us within this field? Well, because root 2 times root 2 is 2, and that just gives me 2 BD, and that's going to be rational. Yeah, so AC plus 2 BD is rational. And then BD plus BC is also rational. So when we multiply 2 elements of Q root 2, we get an element which is in Q root 2. What about division? How do we divide surds? You rationalize the denominator. And to rationalize the denominator, what do you multiply top? What would I multiply top and bottom by here? I would multiply by c minus d root 2. Okay, and then the top would be fine, and the bottom would be c squared minus 2 d squared, and the top would be in q root 2. Now this question here was guiding people to this idea. We know that if we multiply a plus b root 2 by its kind of what we might call its conjugate, if we were in the complex number world, we would call it its conjugate, then we get a rational number.
How long is this?
Till 7:30. Okay. Can anyone find a theoretical, can anyone get an insight between a connection between this and the complex numbers? So when we had complex numbers, we decided that a family of complex numbers that was closed under multiplication was the set of complex numbers with modulus 1. Can anyone suggest a similar family of q root 2 that is closed under multiplication? And I'll give you a clue. What is the analog to the set of numbers of Z mod 1 in Q2? Think about the step of rationalizing the denominator. What do we do with complex numbers to not rationalize, but sort of, I don't know the word, realize, realify, kind of realize the denominator? What special complex number do we multiply by? Yeah, a minus bi, the conjugate. Yeah, so in the complex world, a times a star is equal to the modulus squared. Okay, and in the complex world, the moment we know that AB conjugate is A conjugate B conjugate, that's how you can prove that the modulus is multiplicative. Yeah, because AB times AB conjugate is AB squared, but AB conjugate is A star B star. And then if we just reorder it, we get A star A, B, B star is equal to AB squared, but this is just A squared times B squared. But let's now work in the, if we're inspired by that, okay, if I take A plus B root 2, and I'll call that sort of Z. If I call Z star a minus b root 2, then z star is a squared minus 2b squared. And I could call that the modulus. So I could call this n of z all squared. Yeah, so I just want to use n rather than modulus because for real numbers, the modulus means something different. Okay, but is it the case that a b star in this world is a star b? So let's check. So if z equals a plus b root 2 and w equals a minus b root 2, sorry, c plus d root 2, what is z star w star? Well, it's just a minus b root 2 times c minus d root 2. And when we multiply out the brackets, the rational terms are the same as if we'd had a plus and a plus, but the irrational terms end up with a minus. So that is just zw star, because if I'd multiplied z and w, the only difference is that I would have had a plus here rather than a minus. Okay, so algebraically, if I multiply two numbers, if I multiply two numbers a plus b root 2 and c plus d root 2, then the things square. In particular, what happens if I multiply, if n of z equals n of w equals 1, then nzw equals n of z times n of w, which is 1 times 1. Okay, so zw, so n of zw is equal to 1. So we've got this important observation. The set of a plus b root 2 such that a squared minus 2b squared is equal to 1 is closed under multiplication. So we found one element of this set by inspection. 3 plus 2 root 2 is in S. Can anyone tell me other numbers which are in S? So just to recap what I've done, while you think about that, just to recap what I've done before. I've taken insights from the complex numbers where we found out that complex numbers of modulus 1 were closed under multiplication because the modulus was multiplicative. We then found that this quantity, so the quantity that we get when we multiply by the conjugate, in this field, the q root 2 is c squared minus 2d squared. We realize that if we think of c squared minus 2d squared as being like the modulus, we realize that this quantity is also multiplicative. So again, if this quantity is 1, then if we multiply two numbers with modulus 1, we get numbers which are modulus 1. Now we've got a number which has got modulus 1, 3 plus 2 root 2, just by inspection. Can anyone give me a second number in S? Right, someone's told me 17 plus 12 square root 2. How is 17 plus 12 square root 2 related to 3 plus 2 root 2? So 17 plus 12 root 2 how is it related to this number, 3 plus 2 root 2? What mathematical operation can I do to 3 plus 2 root 2 to get 17 plus 12 root 2? Yeah, I can square it. Yeah, let's just check that. If I square 3 plus 2 root 2, I get 3 times 3, which is 9. I get 3 times 2 root 2, which is 6 root 2. I get 2 root 2 times 3, which is 6 root 2. And then I get 2 root 2 times 2 root 2, which is 8. So I get 17 plus 12 root 2. Okay, so in the chat, can you do one of two things? Can you explain now why the fact that 17 plus 12 root 2 means that 17 plus 12 root 2 is in S? And can you explain to me how I could find another element in Q root 2, sorry, which is also in S? No, well, someone said Pell's equation. So what we've shown here is that 17, so far we've got from Pell's equation is this. Pell's equation is the equation a squared minus 2b squared is equal to 1. And at the moment, we've got two solutions. We've got a equals 3 and b equals 2. And then we've got a equals 17 and b equals 12. Solving Pell's equation would be getting all values of a and b. Now, at the moment, we've got 2. Now, earlier on, we had 2, but earlier on, we only had 2 because we just spotted 2. What we've got here, which is much better, is we've got a way of generating more. Someone's given me a bigger solution, but can anyone give me a method to generate more solutions? Right. Sabine said 3 plus 2 root 2 cubed. Okay. Why is 3 plus 2 root 2 cubed going to be a solution, lead to a solution of Pell's equation? What important algebraic, yeah, and Samuel said take a power of n. Why? What algebraic, so people are now saying like powers of 3 plus 2 root 2. Why are powers of 3 root, try and express it in this new mathematical language that we're getting. Why are powers of 3 plus 2 square root 2 going to lead to solutions of Pell's equation? So it's multiplication. And what have we shown that's special about multiplication? Yeah, it's this blue box here. Look at this look at what this blue box says. It says that S is closed under multiplication. So if we find an element of S and we multiply it by another element of S, we get a new element of S. Okay, now 3 plus 2 root 2 is in S, which means that 3 plus 2 root 2 is in S. And then because S is closed under multiplication, if I multiply 3 plus 2 root 2 by 3 plus 2 root 2, I stay in S. Okay, so that it's this closure property that guarantees that 17 plus 12 root 2 is in S. But if 17 plus 12 root 2 is in S, if I multiply it by another element in S, like 3 plus 2 root 2, I should stay in S. Okay, so 3 plus 2 root 2 times 17 plus 12 times 17 plus 12 root 2. So that's 51 plus 34 root 2 plus 36 root 2 plus 2 root 2 times 12. So that's 24 times 2 plus 48. So we get 89 plus 70 root 2. Okay, now I don't think we would have spotted it, but that means that A equals 89 and B equals 70 is another solution of Pell's equation. Okay, and then I can get bigger and bigger solutions by just doing 3 plus 2 root 2 to the n. If that's equal to A plus B root 2, then A squared minus 2B squared is equal to 1. And as an exercise, this is actually generates all the positive solutions to Pell's equation. Why is this super cool? So you can check it on a calculator if you want, but why is 89 squared take away 2 times 70 squared equal to 1? Why is this cool? What do we know? Tell me a fact about the square root. Yeah, because maths is cool. That's a good answer. What do we know about the square root of 2? Someone asked you to say a fact about the square root of 2. What can you? Yeah, it's square root of 2 is what type of number? It's irrational. Okay, so there's no fraction that equals the square root of 2. But can anybody give me a fraction based on this fact that is going to be very, very, very close to the square root of 2? This type of observation, this observation came up exactly on a math paper. I'll have a look at the year it came up. But what happens if I divide by 70 squared? If I rearrange this slightly, I get 89 squared over 70 squared is equal to 2 plus 1 over 70 squared. So what can you tell me about the number 89 over 70 to a very good approximation? So 70 squared is like a big, big number. So this is going to be 2 plus some, so 1 over 70 squared, what is it, like 1 in 5,000? It's going to be very close to 2. Okay, now if I've done, I'm just going to use a computer to do 3 plus root 2 to the power 10. 3 plus 2 root 2 to the power 10. That is 22,619,537 plus 15,994,000 428 root 2. Now we know that that's going to be a solution of Pell's equation, so we know that 22,619,537 squared, take away 2 times 15,994,428 squared is equal to 1. Okay, so this fraction 22619,537 over 15,994,428 is a real near miss to the square root of 2. So what we've got here is a recipe that, although it's the fact that the square root of 2 is irrational, we can get a rational number that is exceptionally close to the square root of 2. Exceptionally. Okay, in fact, as good as we want, because we can just keep taking higher powers of this special number 3 plus 2 root 2, and then we can just get massive solutions, and those massive solutions are really good approximations, really good approximations to root 2. Okay, I should look up the MAT question, but the MAT question just got you to verify, and it was a little bit rabbit out of a hat, that if you had, that if an squared minus 2bn squared was equal to 1, then if you define an plus 1 as 3an plus 4bn, and bn plus 1 as 2an plus 3bn, that an plus 1 squared minus 2bn plus 1 squared equals 1. That's what the math question asked you to do, and then it just got you to solve start the recurrence with 3 plus 2 root 2 and get solutions of Pell's equation, and then justify that as you went further, you got better and better approximations to root 2. If you've ever looked at that math question and thought, where did Mr. Matt, the person who wrote the math paper, get this recurrence relation from? This is the algebraic structure that lies behind it, and I think this is, I hope this whets your appetite for maths or physics at university, because what's happened here is we've realized that in the complex field, we've realized that the modulus is an important function. Then what we did is, the modulus is important. So if we've got this field, q root 2, what's going to be the modulus? So what might be an important quantity in this field? And it turns out that a squared minus 2b squared is an important quantity in this field. I don't quite know. I want to get the physicists excited at this point. But it reminds me of a conversation that I had a little bit earlier in this call with Mia about when she said, like, can we think about the points on a hyperbola? and I made this connection between, you know, it being a similar question to finding points on a circle. Well, it turns out that traditional geometry, so in normal Euclidean geometry, the correct notion of distance is that distance squared is x squared plus y squared. Or if we have 3 dimensions, it's x squared plus y squared plus z squared. And that leads to the geometry of a circle or a sphere. In the natural space-time geometry, which sort of Einstein and people like that studied, turns out to be that when you introduce time, you introduce it with a negative and you get a hyperbolic geometry. And so understanding that hyperbolic geometry, it turns out that it's important to understand the algebra of a hyperbola. And I don't know if there's really quite a connection between this and Pell's equation, but we can see here that this is like, you know, this is an analogous problem. You know, Pell's equation is an analogous problem to finding Pythagorean triples, but in a sort of hyperbolic rather than a circular world. I don't know if I'm saying something profound or a bit nonsensical. But my point, so my intention with this early bit of the webinar was to really zoom in on mathematical structures, so fields, looking at closure properties, looking at how your mathematical journey of going from natural numbers to integers, to rationals, to complex numbers gives more and more closure properties, finishing with the complex numbers, which is a field which is algebraically closed. So it gives you kind of, in some sense, all the numbers that you need. This bit on Pell's equation was just meant to show you how stuff that you found that is important within the complex field, like the modulus function, that finding like something which is an invariant or which has got like an algebraic property like being multiplicative is always useful. And so you can apply a similar sort of idea to a different field. So this field, which is the rationals augmented with root 2. This field is something which is studied in its own right. It's this kind of idea of just like doing field extensions, adding like roots of polynomials one at a time leads to a branch of mathematics called Galway Theory. And so what I've kind of tried to show is that if you understand the underlying algebraic structures, you end up solving questions using kind of complex algebra idea that don't look like they've got anything to do with complex numbers. Okay, does anyone have any questions about what I've done so far, or what I've done in this part of the webinar? It's a very different style of webinar to last week. So last week's we were looking at like questions very like the sheets where we're doing like lots of calculations. This webinar has been very conceptual, and if you look at the direction that Matt is going for the maths applicants, Matt is becoming more and more conceptual in nature, and while you don't need to know stuff like closure, exposure to those sort of ideas. No questions. People find that interesting? Are people happy they can now solve Pell's equation? if you want to check whether you've understood the solution of Pell's equation, see if you can think about what you would do to find solutions of a squared minus 3b squared equals 1. Okay, but if people are happy, I'm now going to look in the sort of 10 minutes that are remaining. I had planned, I'll show you what I had planned. Okay, I was going to look at some actual sort of complex numbers questions, and I found this sheet shared by Cambridge University, which is a compilation of step 3 questions on complex numbers. Okay, so you can Google this. This is maths.org step. This is step support program, and this is complex numbers questions. Okay, we're probably going to only have chance to do one of them, but yeah, we can do a step question in 10 minutes, I'm sure. So question number 1. For any given positive integer n, a number a is said to be a primitive nth root of unity if an equals 1, and if there is no integer m such that 0 is less than m is less than n, and am equals 1. So write down the 2 primitive fourth roots of unity. So let's first of all consider the fourth roots of unity. So if e to the I theta to the 4 is equal to 1, that means that e to the I theta to the 4 is e to the 2 pi I k. Yeah, because 1 has got argument 0, or if you're being perverse, it's got argument 2 pi or 4 pi or 6 pi or 8 pi. So e to the 4i theta is equal to 2 pi I k. So 4 theta equals 2 pi k. So theta equals pi k over 2. Okay, so the values of theta are, if k is 0, is just 1. If k is 1, then theta is pi over 2, so we get I. Then if k is 2, theta is pi, which gives me negative 1. And if k is 3, we get negative I. Okay, the other way we could do this is we could just get the kind of primitive root. So we just want e to the I theta to the 4 is e to the 2 pi I. So we get 4 theta equals 2 pi. So we get theta equals pi over 2, which is I. And then we just remember that the fourth roots of unity are going to form a square. Okay, so we've got 4 fourth roots of unity, as we would expect, but not all are primitive. Well, 1 is certainly not primitive, yeah, because 1 to the power 1 is just equal to 1. Negative 1 is certainly not primitive fourth root, because negative 1 is a primitive second root, yeah, because if I square negative 1, I get 1. But if I think about I, it is a primitive fourth root, because if I consider the powers of I get I squared is negative 1, I cubed is negative I, and then I to the 4 is equal to 1. So the first time I to the 4 is equal to 1 is the fourth power. So I is a primitive root. Okay, now if you were doing this step question for sort of real, okay, you're probably getting sort of ideas of like coprimality in your mind, yeah, that the second power of I is not a primitive root because 2 is a factor of 4, so you only need to square it. The first and the third, 1 and 3 are coprime to 4, so to get them to a multiple of 4, you really need to multiply by 4. Okay, so notice that I've written far too much because it just said write down the two primitive fourth roots of unity. So I wouldn't need to write this all down. I could have just written down that the primitive fourth roots are I and negative I. It then says let Cnx be the polynomial such that the roots of the equation Cnx equals 0 are the primitive nth roots of unity, and the coefficient of the highest power of x is 1. And it's got no repeated roots. Show that c to the 4x equals x squared. Well, we want a monic polynomial which has just got roots of I and minus I. And it's easy to write down a polynomial which has got roots of I and minus I and nothing else and nothing repeated. It's just x minus I and x plus I. Okay, so that gives me x squared plus 1. Okay, part I. Find c of 1 of x, c of 2 of x, c of 3 of x, c of 5 of x, and c of 6 of x, giving your answers as unfactored polynomials. So c of 1 of x, we just need the primitive root of x to the 1 equals 1, and that's just 1. So c to the 1 of x is going to be equal to x minus 1. C of 2 of x, okay, we want the primitive roots of a squared equals 1. Now, a squared equals 1, a is equal to 1 or negative 1, but 1 is a root of order 1. So we don't want the 1, we just want the negative 1. Okay, c of 3 of x. Well, what are the complex roots of unity? Well, 1/3 root is just going to have argument 120 degrees, because if you cube it, if you cube a number, you triple the argument. So we get a root here. We also get its complex conjugate. There's another cube root, which is 1, but that's not going to be a primitive 1. So the two primitive roots are omega and omega squared. So one way of finding C3 of omega is x minus omega, x minus omega star. And so one thing we could do is we could just find omega using trig. And then we could expand this bracket. But can anybody give me a much simpler way of finding this polynomial without needing to find omega and omega star? So can anyone think of a much simpler way of finding a quadratic which has got roots omega and omega star? So someone's asked in the chat, what does primitive mean again? So a primitive cube root is a cube root that is not a root of a lower order. So it's not a square root, or it's just not 1. So the primitive cube roots are these two, because you really need to cube them. We wouldn't call 1 a cube root because 1 is just 1. So one way of finding this polynomial x minus omega star would be to use trig, but there's another way. Can someone give me a very simple polynomial that is satisfied by 1 omega and omega star? Well, we know that 1 omega and omega star satisfy x cubed equals 1, which means they satisfy x cubed minus 1 equals 0. But we can factorize x cubed minus 1 as x minus 1, x squared plus x plus 1. Now, what's the root of this polynomial? The root of this polynomial is 1, which is boring, because it's just not the real cube root. But this quadratic has got the 2 real cube roots. So C3x, the easiest way of finding it is just saying that it's x squared plus x plus 1. Okay, let's do C4 of x by a similar method. Okay, C4 of x, we've got x to the 4 minus 1 is equal to 0, which factorizes as x squared minus 1, x squared plus 1 equals 0. But x squared minus 1 factorizes as x minus 1, x plus 1, x squared plus 1. The root here is 1. That's not a primitive fourth root of unity because we've already picked it up. Yeah, it's a boring root. X plus 1, that's got root negative 1, but that's not a fourth root of unity. That's a square root of unity. Okay, the remaining polynomial are the 2 real fourth roots of 1, or the primitive fourth roots of 1, I and minus I. So C4x is x4 plus x squared plus 1, which is what we found earlier. C5 of x, we get x to the 5 minus 1. If we factorize it, we get x to the 4 plus x cubed plus x squared plus x plus 1. But for fifth powers, all of the roots are primitive. Okay, because we get a pentagon of roots. This first one, if we square it, we get to the second one. If we cube it, we get to the third one. If we fourth power it, we get to the fourth one. We need to do 5 powers to get all the way around. If we start at w squared, if we square it, we get to the fourth one. If we cube it, we get to the 6th one, which is really the first one. If we fourth power it, we get to the third one, and we only get round to the edge when we get to the 5th power. So this whole polynomial here, x4 plus x cubed plus x plus 1, is satisfied by the primitive roots. Okay, and there's an observation that should be coming into your mind now, that the reason we got all primitive roots was because 5 is prime. With 4, the factors of 4, like 2, led to a non-primitive root. And so then next part of part I said find c to the 6i. So let's consider x to the power 6 minus 1. Well, that's x cubed minus 1, x cubed plus 1, difference between squares. X cubed minus 1 is x minus 1, x squared plus x plus 1. X cubed plus 1 is x plus 1, x squared minus x plus 1. Now, what have we seen before? This polynomial x minus 1 just gives me 1, which is the boring first root. This polynomial we've seen before, it's given me the 2 cube roots. This one we've seen before, it gives me minus 1. But this polynomial is new. Now let's think about the 6 roots of unity. So we get a hexagon. But let's think about the things on my hexagon. This is just 1. These 2 are the 2 cube roots because they've got argument 120. This is minus 1, which is a square root. So the only 2 roots we've never seen before, the only 2 new ones are here. And they are what's satisfied by this polynomial. So that's C. So C6 of x is that new polynomial. Okay, and you should see that every time we do a factorization like this, we get c to the 6 minus 1 is c1 of x, c2 of x, c3 of x, and c6 of x. Okay, and that's because the 6th roots of unity correspond to primitive roots of the factors of 6. So the factors of 6 are 1, 2, and 3. Okay, so the new polynomial that we've never seen before is going to be C6 of x. Okay, this question goes on. It asks us to make an observation about Cp of x. Notice that it just says find an expression, so you just need to guess what Cp of x looks like, and then there's an algebraic thing to prove. But because we've gone a little bit over, I'll leave this question as an exercise, and this sheet, this step 3 sheet, is also a good one to work through. I just had a look at the chat. People said, just going back to the stuff about Pell's equation, people said they weren't sure where 3 plus 2 root 2 comes from. Oh yeah, sorry. So the 3 plus 2 root 2, okay, where did that come from? Well, that just came from, you know, observation. If you stare at this long enough, then you can see that 3 and 2 work. Okay, so if I write down a Pell type equation like a squared minus 3b squared equals 1, okay, I again just need to try and stare at this long enough to try and get something that works. So let's do a race. Who can find something that works first? I can do one. I've got a equals 2 and b equals 1. Yeah, because 2 squared is 4 and 4 minus 3 equals 1. Using a similar logic as before, if I square 2 plus, that becomes my seed. Okay, and then if I square it, I'll get a bigger solution, and that becomes 7 plus 4 root 3, and that should give me a solution of this new Pell type equation. And so I get 7 squared minus 3 times 4 squared. That's 49 minus 48, which is equal to 1. And what that means is 7 over 4, which is 1.75, is a better approximation to root 3 than 2 over 1. But if I was to do it again, I would get an even better approximation. So I could do a similar thing, 2 plus root 3 to the n, to the 10 would give me an excellent approximation to root 3. Just a little historical note. The mathematician Pell, you've got to do quite a lot of work to get your name, something named after you. Pell was able to show that for any value of n here, he actually found a procedure that would give the first solution. Okay, but I'm not going to do that today because we've already done a lot of maths. Okay, but so in answer to the people's question of where did 3 plus root 2 come from, 3 plus 2 root 2, it just came from observation. Okay, sounds like I've run a little bit over. Sounds like dinner is ready downstairs, so I'm going to finish off at this point. I hope people have enjoyed it. Any final comments? Lots of thank yous, which is nice. Yeah, different style webinar today, very, very conceptual. I'm a mathematician by background, so I'm just doing my last little pitch to maybe switch some physicists over to applying to maths or something like that. But yeah, I'm just going to say bye-bye, and I'll see you again soon. Okay, bye-bye, everybody. I'm going to end the meeting for all.